Welcome to Fisher Controls Educational Services Video Training Program. We hope you find that the information in this course helps you to perform your job more efficiently and with greater understanding. This videotape presentation has been developed in coordination with a corresponding student guide entitled Process Control Basics. Whether you read the entire student guide before watching this tape or read it section by section as you progress through the tape, it is a good idea to follow along with the guide as you view this presentation. This is the first unit in the study of fundamentals of process control, which is an introductory course designed to familiarize you with the rationale, terminology, and techniques involved in the control of various types of industrial processes. There are many types of industrial processes used in a wide variety of applications, and therefore there are several distinct standards applied to different segments of the total industrial spectrum. Three major standard-setting groups are SAMA, the Scientific Apparatus Manufacturers Association, ISA, the Instrument Society of America, and ASME, the American Society of Mechanical Engineers. Each of these groups has a slightly different way of defining the term process. For the most part, the differences arise in considerations of where the boundaries of the process are drawn. For example, one definition of a process includes all of the hardware involved, including all valves, transmitters, and other control loop instrumentation, plus the fluid stream itself, but excluding the controller. You'll notice that in this configuration, the controller provides an input to the process and in turn receives an input from the process transmitter. Another definition, as set forth by SAMA standards, considers the process to include only the fluid stream within its piping constraints. Obviously, this description would have to include information about the geometry of the containing vessel, properties of the fluid, and the manner in which the containing vessel relates and interacts with its environment. While this definition is perhaps the purest and cleanest means of considering the concept of a process, it presents difficulties in measurements and therefore is not the most practical and can create problems in the design of control strategy. There are many key factors that contribute to or arise from the operation of a process. One of the most important of these factors is gain. Gain generally is taken to mean the change in output of a device or process divided by the change in the input that caused the change in output. Gain can be expressed in terms of various units of measurement, such as inches of valve travel, degrees of temperature, or cubic feet per minute of flow, just to name a few. Gain can also be expressed as percent of change. Each of these expressions identifies an aspect of gain and the corresponding process output change. Using this ratio of the change in output divided by the change in input, the process gain can be computed over any portion of the operating range of a process that has reached steady state. To use percent in computing output gain, both the input and output spans must be defined. Therefore, gain equals the change, or delta, in output percent, divided in the change in input percent, which is to say the actual change in output divided by the total range of output divided by the actual change in input divided by the total range of input. The output range is the calibrated span of the sensor, which is typically 4 to 20 milliamps. An example of a pure gain process is seen in this jack shaft, which is used in systems controlling the combustion rate in boilers. The jack shaft rotates in response to boiler load demand. opening or closing both fuel and air valves simultaneously, according to the degree of rotation of the shaft. Notice that the air valve changes more than the fuel valve in response to the same input, shaft rotation, due to the difference in the length of the levers on the shaft. Since the output change of the air valve is greater than the input change, the air valve is said to have a higher gain. Since the length of the levers on the jack shaft are fixed, so is the ratio between air and fuel that enters the boiler's combustion chamber. As shown on this chart of a pure gain process, the output change, or gain, is virtually instantaneous, a straight vertical line. In fact, and particularly at high frequencies, a slight delay or lag may become a factor, as we'll see later in this unit. The next process factor to discuss in this unit is dead time, which refers to the length of time between the point at which the input to a process is initiated and the subsequent point in time at which the first effect of that change is observed in the process output. For example, here, we initiate a step change in the process input and identify this point in time as 0. Later, at this point, we see the first change in output responding to that input change. The interval or delay between these 2 points is our process dead time. Process dead time or delay usually reflects the time required for transport. For instance, consider a process involving laminar flow through a pipeline in which the fluid enters the pipeline here at a certain density as monitored by an input density transmitter. Another density transmitter is positioned at the output downstream. Assuming that both transmitters have the same measurement span, we should be able to measure the time between the change in fluid density at the input and the corresponding change in density at the output. If we chart this process and call the time of input change T sub O and the time of corresponding output change T sub 2, then the process dead time, which is designated as tau, will be T sub 2 minus T sub O. Another term to describe the delay in the full development of gain is lag. Pure lag is a process response that is not instantaneous due to the time required for the process output to reach a new steady state value. The time constant is the time required from the initial change in process input for the process output to reach 63% of its final steady state value. The time constant is represented by the letter T and may be determined by subtracting the time of the initial change in input, T sub O, from the time at which the output reached 63% of its total change, T sub 1. The time constant and gain are the 2 parameters required for describing a pure lag process. Let's look at an example of a pure lag process in which we assume that the system is at steady state and has a constant downstream demand that results in a steady pressure at the transmitter. If this manual valve is closed, thereby restricting the flow, the measured pressure will eventually increase to some new higher value. When the pressure stabilizes at this higher value, we say that the process has reached its new steady state. Graphing this process, we can see the process dead time, the process gain, and the process time constant. The dead time in this example is 1 second. The gain is 1, and the process time constant, which is also referred to as the process response, has a value of 2 seconds. You will find that most industrial processes can be characterized as first-order lag, that is, having only 1 lag, plus dead time. You can think of these as a pure delay process, followed by a pure lag process. The reason that this characterization is accurate in so many cases is that so many processes naturally involve the transfer of mass, or heat, or both. This means that there is a certain length of time required for the change in heat or mass to move through a pipe or other medium of exchange to the location of the process. At this point, there is time requirement for the full effect of the change to develop. The first order plus dead time process looks like this on a graph. We have a step increase in input at the time t sub o, but we must wait for a period of dead time until t sub 1 for that increase to reach the process. At this point, we can compute process dead time as t sub 1 minus t sub o. At t sub 1, the change in output begins, finally leveling off. Looking back on the curve, we can see that 63% of the change had been realized at this point in time, t sub 2. This information allows us to compute the process time constant, which is the amount of time required for the process to move from one steady state to 63% of a new steady state. The time constant would equal t sub 2 minus t sub 1. A practical example of a first-order lag plus dead time process is a steam heat exchanger. In this diagram, a process liquid feed stream moves through the heat exchanger, picking up heat, which is given up by the steam, which is also moving through the heat exchanger. The output, or controlled variable, is the temperature of the outflowing process feed stream, as monitored by a temperature sensor. The input, or manipulated parameter, is the rate of flow of the steam. We know that the heat gained by the process feed stream must equal the heat lost by the steam, so the control strategy is to adjust the steam flow to match the combined temperature and flow rate of the process feed stream. In this process, the dead time is the interval required for the feed stream to flow through the heat exchanger and reach the temperature transmitter. As the change in the feed stream temperature first reaches the temperature transmitter, the difference between the feed stream temperature and the steam temperature is greatest. As a result, the rate of change in the process feed stream is also at its greatest. As the fluid absorbs more heat from the steam, the temperature differential narrows and the rate of temperature increase in the feed stream slows down until the temperature reaches a new level or steady state. The reason that this is a gradual process is due to the nature of the heat exchanger, which requires time for the steam to heat its pipe path through the device. In some cases, a process may include a number of independent first-order lags in series. These lags do not affect any other lags upstream, but contribute only to subsequent lags in series downstream, and thus to the total rate in change of output. An example of such a non-interacting first-order lag in series can be seen in our previous steam heat exchanger example. Let's assume that the temperature sensor is inserted into a thermowell in the wall of the process piping. Now, we not only have a lag in the change of the temperature of the feed stream, but we also must consider a lag necessary to heat up the thermowell. Since we have two non-interacting lags in series, this makes the process a second-order process. 3 such lags would be third order, and so on. Anything more than first order is called a higher order process. In most situations, higher order lags are represented as a region of dead time, followed by a first order lag. For example, we see the first order lag in this graph with no dead time apparent. Now we plot the curve of the second order process and see that the first portion of the curve is horizontal, indicating a dead time. The third order process curve has a different shape and different values, but it still can be characterized as a region of dead time followed by a first order lag. So far we have looked at processes in which the output gradually levels off at a new steady state following a step increase in input. Because of this characteristic, these processes are called self-regulating processes. It follows then that a non-self-regulating process is one that responds to a step change in input with an unlimited change in output. Expressing this with a graph, we see that we have a one-time step change in input. As we chart the attendant change in output, however, we see that it does not stop at some level proportionate to the input change, but continues to increase indefinitely, probably until some physical constraint is encountered. The only way to assign a numerical process parameter to a non-self-regulating process is to measure the rate at which the output increases in response to the change in input. This is necessary in order to ascertain how much time is available to respond to the increase before the constraint is reached, since exceeding the constraint usually leads to an undesirable situation. This rate of output change can be either linear, which is to say constant, or nonlinear, which indicates an accelerating rate of change. A simple example of a non-self-regulating process is a tank that is being drained by a gear pump that operates at a constant speed and therefore drains the tank at a constant rate. It follows then that the only way to control tank level is through varying the rate of input into the tank. The output of this process is considered to be the level of the contents of the tank. If there were a controller in this system, it would vary the tank's supply rate in response to the signal of the level transmitter. Without that control, however, this process is non-self-regulating due to the independent operation, that is, constant speed, of the gear pump. Flow from the gear pump will not be able to accommodate changes in the inlet flow, since any increase in inlet flow rate above the gear pump flow rate will result in the fluid level growing until the tank overflows. Any inlet flow rate below the gear pump rate will result in the fluid level diminishing until the tank runs dry. Graphically, we can illustrate the rate of change by plotting the tank level as the y-coordinate and time as the x-coordinate. The slope of this line is derived by dividing the change in y by the change in x. The steeper or greater the slope, the greater the rate of change in level. The rate at which the level rises is affected by the geometry of the tank. For example, let's consider a cylindrical tank. As the level climbs, the surface area remains constant, and thus the rate of change in the level remains constant as well. If the diameter of the tank were smaller, resulting in less surface area, then the rate of change in level would be greater for the same rate of inlet flow, but would still be linear in nature. If, however, we were to place the tank on its side, we would no longer have a linear change in tank level due to the constantly changing surface area, which would increase as the level approached the wider dimensions of the tank, and then began to decrease as the tank narrowed out. Nonlinearity can also be introduced by valve response to differing loads. In fact, the gain of the process is rarely constant throughout the load range or full range of valve travel. As illustrated here, we see that if gas flow were measured at different positions of valve capacity, it is evident that the rate of flow is nonlinear. By establishing a series of flow rates for given valve capacities, we can calculate the gas flow rate gain after steady state has occurred. Basically, the gain at any one point is reflected by the slope of the curve. In this example, the point on the curve reflects gas flow in standard cubic feet per hour, SCHF, at 10% of the valve's total capacity. The slope of the curve at this point is indicated by a tangent to the process curve at a given point. As we know, the slope is computed by dividing the change in the y-axis value by the change in the x-axis value. To compute gain, however, we must compute the y-axis value as a percentage of the maximum flow rate of the valve. So the computation goes like this. The change in x is 5,000 SCFH minus 4,000 SCFH, which equals 1,000 SCFH. This amount is divided by 6,300 SCFH, the maximum gas flow rate, and provides a quotient of 16%. Now we compute our x-axis, which is the percentage of valve capacity. We see that the change in x was from 5% to 14%, a value of 9%. Since this factor is already expressed in percentage of valve capacity, no further computation is necessary to ascertain the x value. The process gain at this point is then computed by dividing the y value, 16%, by the x value, 9%, to yield a gain of 1.7. To demonstrate the degree of nonlinearity of this particular flow rate, let's make a similar computation at a point on the curve that corresponds to a level of 40% of valve capacity. Again, we construct our tangent to the curve at the selected point. Our y-axis shows to be 6,500 minus 5,500, or 1,000 SCFH. Again, we divide this by maximum gas flow rate, 6,300 SCFH, and get an amount of change of 16%. This change in gas flow, however, has required a much larger change in our x-axis, from 20% to 60%, a 40% change in valve capacity. The process gain at this point, then, is 16% divided by 40%, or 0.4. What we see from these figures is the nonlinear increase in valve capacity required to achieve the same increase in gas flow at different flow rates. So far, in this portion of this unit of training, we have learned to identify several of the basic factors that are common to most industrial processes. We defined process gain as the ratio obtained by dividing the change in output by the change in input. Dead time was defined as the time between when the input to a process is initiated and the time in which the first effect of the change is observed in the process output. We learned that lag is a process response that is not instantaneous due to the time required for the process output to reach a new steady state value. We also learned that the time constant, or process response, was the amount of time required for the process to reach 63% of its change between two steady states. We then discussed first-order processes and higher-order processes that could be described as a region of dead time followed by a first-order lag. Finally, we described some specific cases, such as non-self-regulating processes and nonlinear performance. Many processes or control situations are either relatively simple or have already been implemented successfully. Still, there will always be times when it's necessary to develop a solution for a new process situation, or to reevaluate, reconfigure, or retrofit an old one. When this happens, there are hundreds of control alternatives from which to choose in planning your solution. Because of this, you need to approach your problem through an organized method of evaluation to make certain that you choose the control alternative most appropriate to the process in question. When approaching process control problems, there are several things that need to be considered. First, we must thoroughly analyze the total process to understand the nature of its inputs, its internal dynamics, and its output requirements. In doing this, it is always helpful to develop a sketch or schematic rendering of the process to aid in visualizing the relationship of the various components of the process. At this point, the sketch should only include the process itself, without any indication of control valves, sensors, analyzers, controllers, or other instrumentation. In this example, the process sketch shows that water and a slurry are mixed in a vessel. Heat is then added to this mixture through the mechanism of a steam heat exchanger. After the mixture is heated to some specific temperature, it is pumped out of the vessel. Now that we see what the process looks like, we can proceed to the next step in problem analysis, which is to state the objectives of our process control system and to impose a priority ranking upon them. In this particular example, the objectives or process control variables to be considered are as follows. First, control the viscosity of the mixture. Second, control the temperature of the mixture. Third, control the level in the tank. In the development of these controls, you should remember that all processes are subject to load disturbances. A load disturbance is any factor or variable that can have an influence on the final control parameter. To be able to identify and understand process load disturbances, you must first identify and understand the nature of the various loads on the process, especially as the process becomes more complex or interactive. In our example, the loads are as follows: water temperature, water flow rate, slurry temperature, slurry flow rate, slurry viscosity, steam temperature, steam flow rate, mixture demand, and ambient temperature. Now, each of these loads needs to be studied so that the parts of the process that each load affects can be isolated as a basis for developing a control plan. Once this is done, the plan can be visualized by adding appropriate control valves in the process lines where applicable. In evaluating the loads, you should determine its importance and effect on the system. This will help you to determine which variables can be manipulated, which ones are a given, and which ones cannot be controlled. All of these determinations will provide the base assumptions for the final control plan. With this in mind, let's go back through our load analysis and make these determinations for our process. The water temperature is considered a given. The water flow will be manipulated. The slurry temperature is a given. The slurry flow rate will be manipulated. The slurry viscosity is not controllable. The steam temperature is a given. The steam flow rate is manipulated. The mixture demand is not controllable, and the ambient temperature has no effect. Now from this list, we have 3 manipulated variables to apply to control our objectives, which are these 3 process variables: mixture viscosity, mixture temperature, and tank level. Since some or all of these are interactive, a choice must be made in order to match the manipulated variables to the appropriate process variables. So the next important step in our control plan development is to consider one of the 3 process variables and to select the particular manipulated variable that provides the best match with the process variable under consideration. In making this match, we would ideally like to have the process variable respond quickly to whatever change is made in the manipulated variable. In other words, there should be a minimal lag between the manipulated variable and the process being controlled. It is also desirable that the selected process variable be easy to implement. That is, quick delivery may not really be the most important factor. In order to pick the best solution, examine your list of manipulated variables and process variables, and then first make the most obvious choices for solving the control problem. For example, it seems to be obvious that the best control to modify the temperature of the mixture would be on the flow of steam as controlled by the steam valve. That was a fairly simple choice, But as we move to our second choice, it gets a little bit more difficult. We know that we can manipulate the slurry flow rate, but should the slurry valve be used to control the viscosity of the mixture or the level in the tank? Remember, we have another control available in the flow of water coming into the tank, and the controlled input of water will have the same effect as the input of slurry. In this example, it seems to make more sense to control viscosity through the control of the slurry, which becomes our second control match, and to control tank level through the manipulated input of water. An important point of this example is that such choices are not always clear, and the system could still work if different choices were made. As you work to find the best solution, you should bear in mind that there may be 3, 4, 5, or even more solutions that are all equally practical. The choice often boils down to the one that seems most logical and makes the most sense to you. Once you have made the choice in matching the manipulated variables and process variables, the next step is to add the appropriate instrumentation that will implement your control strategy. This includes the selection of controllers, transmitters, transducers, positioners, sensors, and so on. Your first move should probably be to add the instruments needed to create feedback loops. After these are in place, you can begin to address special, more advanced control schemes that may be necessary in cases where there are significant time delays, dead time, or load disturbances that make simple feedback ineffective. Finally, you must analyze each process variable in order to ascertain where the most effective placement will be for control valves, transmitters, and controllers. As you will learn in real-world applications, actually implementing process control is considerably different from just sketching the processes involved on a piece of paper. Nonetheless, the step-by-step procedure we have just described, in which we systematically listed the process loads, sketched the process, and then matched the manipulated variables to their corresponding process variables, will help simplify your decisions when you reach the point of adding feedback control instrumentation in a real application. This exercise also will help you determine whether a more complex control strategy might be appropriate by enabling you to visualize many of the consequences of different load factors and various control actions while they are still on paper, long before they can cause problems in the field.